Hi everyone, and welcome to the 8th ISDE International Lectures. Uh, my name is Sadra Karimzadeh. I'm an assistant professor in University of Tabriz, Department of Remote Sensing and GIS, and also a research fellow in Tokyo Institute of Technology, Department of Architecture and Building Engineering. Well, first of all, I would like to appreciate International Society for Digital Earth giving this opportunity for me to perform a lecture for you. And today's presentation topic is remote sensing of vulnerability, and I will talk about damage estimation of Kahramanmaraş earthquake in Turkey. Well, today here is the table of content. You see that firstly, I will talk about remote sensing and the principles. Actually, I don't know how many people will join to this presentation and how much do they know about remote sensing. So the principles comes at first, and then I will talk about review of past earthquakes studied by remote sensing, and after that Sentinel Asia mission for emergency response, and finally Kahramanmaraş earthquake damage mapping, and also I will show you some field displacement maps of Kahramanmaraş earthquake. Well, also, I divided the remote sensing of vulnerability into two categories. First category is tectonic movements like earthquake vulnerability, earthquake damage, and second is non-tectonic movements like land subsidence and soil consolidation. Well, remote sensing is a technology to acquire information from an object or a feature on the Earth's surface without any physical contact, only through electromagnetic waves. So, this is a new emerging technology in the recent decades. It has high performance, fast actions. You don't need many labor works, and also it is rather cheap technology comparing to field sensing. And remote sensing uses different wavelengths in different bounds, as you can see in the picture. Radar wavelengths are considerably longer than visible wavelengths, as you can see here. Let me show you. Here is the visible range, as you can see. And you have many attenuations, as you can see here. There are water vapors, other particles suspended in atmosphere, so the attenuation will be high. But if you come to the left side, you will see microwaves here. Longer wavelengths and smaller frequencies. You see here this area. You don't have much attenuation. You don't have obstacles like water and carbon dioxide here. So you can use it in all weather conditions, regardless day and night. You can use it. And clouds or other obstacles are not important here. And also sensors use different bounds for different purposes. You see, for example, in shorter wavelengths like X-band, you have low penetration. So if you would like to acquire information from canopy of a tree, this is ideal. But if you need more penetration, you may use longer wavelengths like P-band or L-band. For example, ALOS-2 satellite uses L-bound with like 24 centimeters because the JAXA and Japanese organizations know that Japan is a green country with a dense vegetation and forests, so they need more penetration in order to acquire useful information. Okay, so here, if you take a look in the left and right picture, you will understand the meaning of passive and active remote sensing as well. In the left, you see passive remote sensing or optical remote sensing. You have a light, or let's say sun, a source of energy, and your eyes are acting like camera or sensors, optical sensors. Then you will see the apple and you obtain useful information. Yeah, this is a fruit and its name is apple and the color is red, so this is quite good. But in absence of light, you cannot use your optical sensors, I mean your eyes. So you touch it. This touching is SAR, or synthetic aperture radar remote sensing, or let's say active remote sensing. So you touch it and you understand that this is a fruit and the name of fruit is apple. But of course you don't know about the color of apple. So this is a disadvantage. So I would say that, yeah, optical and active remote sensing are complementary to each other. That's all. So about the SAR remote sensing of vulnerability, the concept is clear. As you can see in the left side, you have an intact building, you have a destroyed building. As seen by nadir-looking optical sensor, if you have a gable type rooftops, the rooftops are similar, but as seen by INSAR, or the phase difference of radar images, you will understand there is a phase difference. So this phase difference is important and we can use it to understand the extent of damage. So as you can see in the right side, you need at least 3 images in time T1, T2 and T3, and then 2 repeat cycles for INSAR or interferometric analysis between T1 and T2, let's say first cycle, and also T2 and T3 as a second cycle. And you see that disaster like an earthquake happened between time 2 and time 3. Also, you can use this technique for non-tectonic movements like land subsidence or other movements. These are how we can use phase information. Later I will also talk about intensity information. You know that SAR has 2 components, amplitude, or let's say intensity, or backscattering signals, and also phase information. So here you see 30 SAR missions, many different missions, and Sentinel NVSAT-ER is from European Space Agency, and ALOS-1, 2, and more recently ALOS-4 from JAXA. ALOS-4 has not yet launched, but maybe planned to be launched soon. You see the repeat cycle, minimum repeat cycle by days, and also maximum spatial resolution. NISAR is also coming, a mutual project between NASA and ISRO, Indian and US administrations. Well, here I sorted the remote sensing of vulnerability studies until 2011. It is started from Kobe earthquake in 1995. You see many works have been done here. Matsuoka and Yamazaki in 1999. We are working together for the upcoming events as well. Other earthquakes, Gölcük and Kocaeli earthquake in Turkey, Izmit again in Turkey. Other earthquakes like Chichi in Taiwan, in Bam earthquake in Iran, and other earthquakes until Tohoku earthquake in Japan. But after that, I also started to getting involved in such damage mapping projects. My first, and this is my personal activity, you see here, my first event was Aharvarzagan earthquake in Iran in the year 2012, and the results are published in IGAR's conference in Fourth Force. Other earthquakes like Amatrice in Italy, Kumamoto in Japan, Kermanshah earthquake 2017 in Iran again. You see also the outcomes here, the published papers. Eastern Ibori earthquake again in Japan, Petrinja again in Croatia, and more recently the Kahramanmaras earthquake in Turkey. So following upon a request from AFAD, Disaster and Emergency Management Presidency of Turkey, we started to produce some critical damage maps for AFAD. And these all activities are happening under the umbrella of Sentinel Asia. Sentinel Asia is a mission for disaster, how to say, damage mapping of the Asian countries, because I don't know how many percentage, but a lot of damages and casualties of natural hazards are related with Asian countries. So this is the main purpose of the Sentinel Asia mission. You see here the framework of Sentinel Asia in 3 steps. First pilot project started in 2006. For 1 year it was pilot project, and after the learned lessons, the second step started in 2008 for like 4 years. And after emerging of new technologies and new satellites, new information technologies, the third step started by joining new members, different countries and their institutes or universities. Also, you see here concept of Sentinel Asia in 3 steps: pre-disaster for mitigation and preparedness, like early warning system, and just after disaster, like disaster response or emergency observations, like what we did for Kahramanmaras and also other earthquakes. So this is just after disaster, and also post-disaster activities like recovery monitoring, the reconstruction period, all under umbrella of Sentinel Asia. And then they provide a web GIS information sharing system for the stakeholders, for the organizations, for the decision makers, the end users. Well, for the Kahramanmaras earthquake, we used also intensity information, as I told you before. Here is the basic approach, and the figure shows details. You see, if you have a pre-event situation and the intact building, you have a double bounce and a strong reflection. But in case of a collapsed building, as you can see in the right side here, you have more scattered signals, so you will receive a weak reflection by sensor. For this technique, you don't need 3 images, you need 2 images at least. And this is one difference between when you use phase information with when you use intensity information. What we do here is image matching and speckle noise filtering, and you have 2 variables: difference of backscattering coefficient between pre-event and post-event images, and also correlation coefficient. So if you are interested in details, you can take a look on these papers, Matsuoka and Nojima, published in Remote Sensing 2010. Also Karimzadeh and Matsuoka 2017, and also Karimzadeh et al. In 2018. So we have two variables, intensity difference, as I told you, and correlation coefficient. And we also have two functions. One is a discriminant function coming from regression analysis, z-score, as you can see here, and also likelihood function or fragility curves to estimate the severity of damage. Well, here are the developed functions using ERS1. Of course, we didn't develop these equations. This happened before in Matsuoka and Nojima paper, ERS1 and GERS1 datasets used for these equations. You see here the coefficients. D is intensity difference and R is correlation. And in the below figures, you see the fragility functions or likelihood functions of 7 damage states or 7 damage degrees, as you can see for two functions. And here is the relationship between ZR or discriminant score and damage ratio for only JERS average, for only negative JERS average, positive standard deviation and average, and also for ERS. You'll see this. And here is the flowchart, as you can see. Pre-event, post-event earthquakes, multi-looked, co-registered, and speckle noise reduced using a Lee filter, 21 by 21 pixel window size. And then we have two variables, as I told you, difference of backscattering coefficient from equation 1 and the correlation coefficient from equation 2, and then we developed discriminant scores like this, and then we masked the urban areas using global urban footprint datasets of the TLR, and then we developed the damage degree model. And here you can see the used dataset, Pulsar 2, ScanSAR imagery. We have a very large footprint in the ScanSAR mode of Pulsar 2 images, and you see that almost all of the affected areas in southern Turkey and also northern parts of Syria are covered well with ascending and descending footprints. You see here these black stars are the epicenters of M7.8 and M7.5 magnitudes, and the dates of ascending and descending datasets are here. A spatial resolution is almost 30 meters in HH polarizations. And here you are, this is the discriminant score, ZR map, and these are damage proxy map in different damage states, as you can see in the right side. And some of the mostly affected cities are shown here: Antakya, Kahramanmaraş, Gaziantep, Malatya. Other cities, for example in Adana, not severe damage observed. Kirkhan, Islahiye, Nurdağ, Adıyaman. Again, other cities. And some cities in northern Syria, Aleppo, Latakia. Well, and the details of this work will be presented also in 18th World Conference on Earthquake Engineering on July 2024. And here is also interferogram of Kahramanmaras earthquake extracted from Sentinel-1 datasets. You see here ascending orbits. Orbit, I guess, 48. And here again, damage proxy map using face information, coherence information. You see some of the selected areas, Karmanmaras, Iskenderun. And again, other view of damaged areas in Antakya, in Iskenderun, in Kirkhan. And here also you see damage proxy map for Karmanmaras. Red pixels are possibly totally collapsed buildings. And also you can extract useful information about the orientation of buildings, whether they are diagonal buildings or horizontally or vertically constructed buildings. Here, green pixels are diagonal buildings, pink pixels are horizontal or vertical buildings. And mood of cities can be extracted as well. As you can see, we have two windows in here. In the left side, Antakya, in the right side, Gaziantep. Of course, based on this circle, red is direct damage, blue is no change, and green is human activity. So you have more damaged areas in Antakya. But why not damaged areas are green in Antakya, but in Gaziantep most of them are blue? This is because of the human activity. You know, in Antakya after the earthquake, the human activity increased. I mean, a lot of activities related with debris removing or working of the heavy vehicles to remove debris. Because of this, you will see greenish in Antakya, but in Gaziantep everything is calm and there is no direct damage. So you can understand mood of cities. Okay, thank you so much for your time, and thank you again for International Society for Digital Earth.